Hello everyone, my name is Kunyang and I am a graduate student from Georgia Tech. Today I'm honored to talk about my research on the pairing of massive black holes in merger galaxy and its implications for LISA. Massive black holes are believed to live in the center of galaxies, and a tight correlation between the mass of the massive black hole and the bulge suggests a potential coevolution between the black hole and its host galaxy. Furthermore, observers have found a higher dual fraction toward smaller separation, which indicates a possible relation between the merger of galaxies and the triggering of dual. This image shows NGC 6040, one of the confirmed dual system in our universe. We haven't observed a lot of this system, mainly due to the resolution and the observing technique, which always requests follow-up observations for confirmation. So among all those massive black hole pairs, some of those will eventually merge and emit low-frequency gravitational wave, which can be picked up by LISA. So overall, it is fairly important to study the problem of massive black hole orbital decay. There are a couple questions worth asking: whether a pair of massive black hole will merge or not, and if they merge, how long will it take? And if any galactic property will affect this process. So we built a semi-analytic model to study this question. Our galaxy model contains a primary black hole that is fixed at the center of galaxy remnant, and a stellar bulge around it, a stellar disk, and a gas disk. Our secondary black hole orbits the primary one in the disk plane, so it's a two-dimensional problem. The total mass of the bulge is 1000 m1, following a lot of simulations treatment. And to mimic our own Milky Way, the stellar bulge follow a correlates power law density profile, while the gas and stellar disk both follow a power law in the radial direction. In each simulation, our secondary black hole start with the initial velocity and at a separation of 1 kiloparsec. The simulation stops when the separation reaches below 1 parsec. We have 5 key model parameters in our model. First, the gas disk rotational velocity in the unit of circular velocity. Then we have mass ratio m2 over m1, then the total massive black hole pair mass, which is m1 plus m2, the central gas number density in the unit of particles per centimeter cube, then we have gas fraction. By varying each parameter in the range of interest, we have a whole parameter space that give us in total 4,000 different orbital decay simulations. In the process of orbital decay, we account for dynamical friction. Dynamical friction is illustrated by this little cartoon in the left. If m2 is moving toward left with a velocity v, then no matter the gas or the star banded by the gravity of m2 form a gravitational wake trolling m2, and this wake will generate a dynamical friction which is opposite to the direction of motion. In our model, we take into account the dynamical friction from both star and gas. For stellar dynamical friction, we follow the model in Antonini and Murray 2012, which improves from Chandrasekhar's classical model by account for both stars moving slower and stars moving faster than the secondary black hole. Then for gas dynamical friction, we follow the approach in Kim and Kim 2007, which break the locality and account for the spiral shape of gravitational wake due to the orbital motion of the secondary black hole. So now let's start with a case study. This is the orbital decay results of one of our galaxy model. This pair of massive black hole in the host galaxy have a pair mass of 10 to the 6 solar mass ratio of 0.1, gas fraction of 0.9, central gas number density of 300 particles per centimeter cube, and a gas disk that is rotating at 70% of the circular speed. As shown in the left panel, you can see that the semi-major axis of the orbit gradually decreases as time passes by, and this process speeds up towards the end. The inset plot shows the shape of the orbit, while the color bar indicate the time. We also want to know that which galactic component contributes most in this orbital decay process in the aspect of dynamical friction. So we define a parameter gamma. For example, gamma for gas disk is defined as the time averaged dynamical friction from gas disk over the time averaged total dynamical friction. As you can see in the right panel, when the separation is larger than 30 parsec, the dynamical friction from gas disk totally dominates the decay process. However, when the separation goes below 30 parsec, the stellar bulge generates a larger dynamical friction, and it takes over the decay process. So that was only for one galaxy. Now let's combine all 4,000 different simulations and use all this data to see how different galactic properties will affect the parent probability of massive black hole pairs. We define the parent probability as the fraction of massive black hole pairs that have their inspiral time shorter than the Hubble time, which means they are able to merge within the Hubble time. So, as you can see from this plot, a pair of massive black hole with smaller mass tends to have lower parent probability due to their smaller bulge and less efficient stellar dynamical friction. When the total mass reaches below 10 to the 6 solar mass, the parent probability is nearly 40%, and at 2 times 10 to the 5 solar masses, it's around 15%. It's fairly low. This is the same plot, but showing how the parent probability is affected by the gas fraction. You can see there are two different populations in this plot. One is when the gas fraction Fg is larger than 0.2. Their parent probability are in general lower than 70%. While the other population is when Fg is smaller than 0.2. This population have a fairly high parent probability, larger than 90%. So these two populations are due to the dominant dynamical fraction, because when Fg is larger than 0.2, orbital decay process is dominated by gas dynamical fraction, and when Fg is smaller than 0.2, this is when the stellar dynamical fraction from the bulge becomes significant. So the combination of gas and stellar bulge dynamical fraction speeds up the decay process and makes the parent probability fairly high. From this plot, we can conclude that the parent probability is not affected by mass ratio significantly, as the mass ratio varying from 0.1 to 1, the parent probability only change in the range of 10%. But the parent probability is relatively high in massive black hole pairs of comparable masses. Now, this diagram is really interesting. This shows how the parent probability is affected by the gas disk rotational velocity. We can see that it peaks at negative 0.3 and 0.8. Well, negative Vg means a gas disk that is rotating opposite to the secondary black hole. So the reason behind this is the relation between the magnitude of the gas dynamical fraction and the Mach number. Remember that when Mach number becomes smaller, the gas dynamical fraction's magnitude becomes larger. So for a massive black hole that is moving in circular orbits, its velocity at the epicenter is close to the circular speed. So for a gas disk that is rotating closer to VC, the relative velocity between the secondary black hole and the gas disk is going to be smaller, which makes the Mach number smaller, and the gas dynamical fraction more efficient, which will result in a higher parent probability. And the other peak is for massive black holes in eccentric orbits. In eccentric orbits, the velocity at the epicenter is fairly small, close to zero. So for gas disk that rotate counterclockwise, the slower it rotates, the smaller the relative velocity become, and the larger or more efficient, the gas dynamical fraction becomes, which also results in a peak in the parent probability. So in reality, the dynamical fraction will also be affected by radiation feedback. Radiation feedback is due to the radiation from the accretion onto the secondary black hole. As you can see from this series of plots, here is the secondary black hole at 0, 0, and this is a bubble due to the radiation, a bubble of ionized gas due to the radiation, and as it moves upwards faster and faster, a bulge shock forms ahead of the secondary black hole, and this additional gravitational wave ahead of this secondary black hole will actually change both the direction and the magnitude of the original dynamical fraction on the secondary black hole. So this red dashed line shows the relation between the gas dynamical fraction and Mach number. After accounting for radiation feedback, it actually changed the magnitude to 60% of its original value and reversed its direction. So this red line actually becomes the blue line after accounting for radiation feedback. So now we want to know that with the effect of radiation feedback, how will the parent probability change? As you can see from this plot you have seen it before, but now we include the deep blue stars for the parent probability after accounting for radiation feedback. When the total pair mass is smaller and equal to 10 to the 7 solar masses, the parent probability is reduced significantly due to the radiation feedback. But when the pair mass is larger than 10 to the 7 solar masses, it's nearly unchanged. This is because when the total pair mass is smaller, those systems tend to be dominated by gas dynamical fraction, and radiation feedback only affect gas dynamical fraction. So when the pair mass is large enough, which means it's dominated by the stellar bulge dynamical fraction, taking into account of radiation feedback will not affect its parent probability a lot. This plot shows how the parent probability is affected by radiation feedback. As you can see, when the gas fraction is larger, it seems like the parent probability is reduced more significantly, and this is because radiation feedback only affects gas dynamical fraction. So when a host galaxy contains more gas, it means it will be more significantly affected under radiation feedback. In summary, we built a semi-analytic model to study the massive black hole pair orbital decay under the effect of gas and stellar dynamical fraction. We can also use this model to search for potential LISA sources. We find that galaxies with larger stellar bulge or a gas disk rotating close to a circular velocity will be more likely to host LISA sources. Also, massive black hole pairs with comparable primary and secondary black holes are more likely to be LISA sources due to their short inspiral time. Furthermore, we find that radiation feedback actually reduces the massive black hole pairing probability by in general 40%. And this effect is most severe when the pair mass is smaller than 10 to the 7 solar masses. And this is the range of detection of LISA. So if radiation feedback plays an important role in real galaxies, then the merger rate of massive black hole pairs detected by LISA may be substantially reduced. Here are my references, and thank you for your attention. With this slide, I will take any question you have.